and participate in a career preparation session. Then you will have the chance on August 1st to interact with 15 quantum companies in Europe, US, and throughout the world. We will write all these details on Discord too and on Canvas too, but stay tuned today and work on it the next days. And then you will get in touch with many quantum companies who want your skills. Jibran, please go ahead.
Thank you, everyone. Thank you, Malu. So yeah, I really wish the Q&A session also went on longer. It was really nice to have the tour of the lab and the really informal Q&A. But we have to do Grover. And as Malu mentioned, finish off the QBronze part of the workshop. And so what's really nice, so it's nice. It's a nice departure from our discussion about implementation and physical details. But we get kind of our first look at something that could be really treated as what, from a computer science perspective, is a very cool algorithmic application of quantum computing for algorithmic problem solving. And we'll introduce the problem briefly. But before I get to the details of the problem, one key concept that we want to review from our last discussion was this notion of how we implement any arbitrary classical function using a quantum gate. And we had this notion of reversible transformations or unitaries. And we noted how the key thing would be that if I want to implement any arbitrary Boolean function f, we will have some auxiliary or additional memory. That memory will be used to store this the result of the computation, i.e. the result of computing the function f on this input. So that will be kind of the key thing that we'll take starting off. What we'll need from as a prerequisite from our discussion last time. All right. So what we have is something that kind of happened around the time as Shor as well. Shor's algorithm we'll discuss in QSilver, but Grover's is in some sense a more universal, proven speed up, as we'll discuss in more detail in Silver, that even though there's the potential speed up in with Shor's algorithm is much greater, is exponential, but we don't have it completely proven yet. Whereas with Grover's algorithm, we have a proven quadratic speed up for a specific algorithmic problem. Well, what is exactly the problem? The problem is that of unstructured search. And I'll try to motivate where we are coming from. If you've done any kind of computer science or introduction to programming, chances are you've done binary search. Or even if you haven't done computer science, sometime when looking up some information in a telephone directory, you've done a binary search, right? So if you're looking up a name that starts with an M versus a name that starts with a Z, you kind of know which part of the directory to start looking from, assuming you recall what a telephone directory is, right? Something that's alphabetically ordered, so maybe a dictionary, if a telephone directory is maybe too old. So you kind of partition your logical search space accordingly, because you know the data that you are going to search has been ordered according to some criteria. Grover's algorithm is not doing that kind of search because it assumes that we do not have any structure on our data. That's the unstructured part. So you can assume you've basically just got a huge pile of data that isn't ordered. You can't assume an ordering of, something starts with an A, then something starts with a B, and so on and so forth, or anything along those lines. One nice motivation that relates to computer science applications and probably is easily understandable as well is, imagine I give you a Boolean formula and I ask you, so it has some number of variables, and I ask you, is there an assignment of this formula to the variables x1, x2, x3 that will make this formula satisfiable, right? So a priori, there's no reason why you'd expect there's any kind of structure in terms of how you would search for the assignment of values to these variables in order to get or find a satisfying assignment, right? So imagine if you've got a formula of the form, x1 or x2 or x3 and x4 or keeps going on and on, with repetition possible as well, negation as well. And now you want to say, hey, is there an assignment to these variables x1, x2, x3 such that the entire formula will be satisfied, i.e. evaluate to 1. To the best of our knowledge, this relates to deep computer science problems in terms of classes NP. We don't know whether or not there is a structure to be had in terms of when we're looking for whether or not a formula is satisfiable or not. And so if the best thing we can do is to really just exhaustively apply, all possible Boolean assignments. So you start off, let's say, with 0, 0, 0, 0, all the way up till 1, 1, 1, 1, 1. And if there is a satisfying assignment, you're guaranteed to find it. If there isn't one, it will take exponentially long because there are 2 to the n possible assignments, but then you'll be guaranteed that, hey, I've exhausted my search space and I didn't find anything. So that's essentially unstructured search. So if you imagine I had a Boolean formula, it might be satisfiable via multiple possible assignments, right? If it is indeed satisfiable. And I want to find one such satisfying assignment. This indeed is an example of unstructured search. And the way we'll connect it to our formalism that we've introduced before is, so you assume you've got this black box that I've kind of drawn in blue. What I can do is query this box by providing it as input bit string x. This x is essentially going to identify the values x1, x2, x3 up till x sub n. So it's going to fix a row in this size 2 to the n table, right? And out will come f of x. I don't get any other information about this function f other than the value of the function f evaluate on the input I provided. And the goal of unstructured search is to find this one value, or perhaps one among many possible values, perhaps, x prime, such that on that value x prime, the function f evaluates to 1. The number of times I will query this box in order to determine whether determine a value on which the function evaluates to 1 will then be termed the query complexity of this problem. And I just already mentioned, the classical query complexity in this case is known to be lower bounded by an exponential, 2 to the power n, or if you make 2 to the n equal to capital N, then the big omega sign means it's a lower bound. The big O usually means an upper bound. That means any algorithm that's going to deterministically search for a satisfying assignment using query complexity must, in the worst case scenario, query exponentially many number of times. What we will prove today is that in the quantum case, where I have a quantum version of this oracle, this query complexity can be brought down to omega of square root of n. That's essentially Grover's result. So Grover constructed an algorithm that would solve this problem of unstructured search in times square root of n, whereas the best possible result, and that's kind of what I indicated earlier, that in this case, unstructured search is a problem for which we know that classically the lower bound is 2 to the n. For integer factorization, that will do for sure. We don't actually know what's the lower bound, and that's where there's a bit of open research question there. In this case, we have a provable separation between classical and quantum, i.e. that there's a quadratic speedup. One might hope that this speedup might be improved, but you have also got a proof that shows that Grover's algorithm is optimal. So you cannot do better than square root of n. All right. Right, so this is not big O notation, this is big omega, which means it's just a lower bound. So rather than thinking of it informally as a less than or equal to, which is big O, you can think of it as a greater than equal to. Any classical algorithm that's going to do unstructured search must use greater than equal to order of 2 to the n queries. Okay, so that's the problem that we want to solve. As I mentioned, what we'll use is the quantum oracle for the function that we are going to be searching, encoded in terms of this unitary, which has this additional auxiliary memory. And we will kind of encode this unitary using, and we'll use it using phase kickback that we mentioned last time, which allows us to store the value of the computed function in the phase rather than in the actual encoding of the state. And we'll see how that helps us out, right? So we'll take that as definition. We'll come back to it specifically in terms of application of the Grover algorithm. Another tool that we just need to go through in terms of calculation is figuring out what will Hadamard do on n qubits. We haven't explicitly done that calculation. Many of you may already have an informal idea or actually know the transformation. But for people who haven't seen it before, let's quickly just work through it. We have seen how Hadamard applied to just the 0 state results in this 0 plus 1 state, which we call a superposition of the 2 states, which we also write as just the plus state. Similarly, for 1, we write it as minus. At some point, we've even seen the computation that what if we applied Hadamard, tensor Hadamard on the 0, 0 state. In this case, you could just quickly do the computation as, hey, this will be just plus tensor plus. And if you multiply, take the tensor product and multiply everything out, you verify that, hey, this is going to be nicely represented as a uniform superposition of all possible 2-bit strings. Well, that's exactly the intuition that we'll have for n qubits as well. What if we had an n-fold tensor applied to n qubits, all of them initialized in the 0 state? Well, you could just write it off as, again, plus tensor plus, oops, n times. You could verify it and prove it by induction if you want, and it's probably obvious as well that this can then be written as this uniform superposition. And this is a notation that we'll use often, writing down Grover's algorithm. So it's nice to just see it first. So it's this is saying that X is a length and bit string. We're summing over all possible length and bit strings. And so this label inside the ket is for a fixed choice of X, that one fixed bit string. You sum over all of them, and then you have a uniform superposition over them. So applying an n-fold Hadamard or applying Hadamard to n qubits gives you this uniform superposition. And that's where you get this popular description of quantum computing, where the algorithm is working on all possible inputs at once. Kind of that idea is coming from the fact that nearly every quantum algorithm would start out creating this uniform superposition, and hence get this ability of applying any future transformation on all possible states, input possibilities in superposition. That doesn't get the problem solved, but that's usually a good start. No questions so far. So here's a brief, concise statement of Grover's algorithm. We'll spend the lecture today expanding it out and going through the computation, but it's relatively very simple to specify. So assume so we won't worry about the auxiliary states for applying the oracle and whatnot. Let's just focus on the n qubits on which we have our input encoded. So let's assume this register X is referring to the n qubits that will store our input. So that's our quantum memory. N qubits that are coming in as input, we start off by initializing them to the all 0 state. And then, as we just discussed, perform Hadamard on all of those qubits. So that's the simple step 1. We already know what would be the result of step 1. It's this uniform superposition of n qubits in all possible length and binary strings. The non-trivial interesting part of Grover's algorithm then is this transformation G that we'll apply on this register X coming out of step 1. So recall, from step 1, we are getting this uniform superposition out. Step 2 is this application of transformation or gate G, where we see a familiar friend, n-fold Hadamard, but you've also got 2 additional oracles, Z0 and ZF. ZF is nothing more but the encoding or the oracle that encodes our function f that we've already been familiar with. And the way we have written it over here, it's already implementing the phase kickback kind of notation. So the function f evaluated at x, you store that information in the phase in front of x. So ZF is nothing more but the oracle for the function f. Z0 is a specific fixed unitary that actually is independent of f. Right, so you note Hadamard is independent of f, and Z0 itself is also independent of f. What is it really doing? It's really just doing something very simple. It notes that, as we've seen previously, X would be in a uniform superposition of all possible bit strings from 0, 0, 0 up to 1, 1, 1, 1, 1. Just in front of the ket labeled by the all 0 bit string, flip the sign in front of it. That's all. Right. If you think about it right now, there's a very nice simple matrix representation for this transformation as well. I'll explicitly write it out later as well. So step 2, the non-trivial part of Grover's algorithm was to first figure out this G. We have stated what that is. And now this additional part is we're saying, hey, apply it k number of times, where we will figure out k later. We are not specifying k right now. We will say, hey, there's this transformation G, and you'll need to iteratively apply it. Think of it as kind of like a loop. apply G so many number of times. This parameter K will depend on some details of the properties of the function F that will become clear in analysis of the algorithm. And once you've applied G K number of times, just measure your X. And with high probability, the expectation is that the result will be a bit string X for which the function F evaluates to 1. Right? Everyone okay with the structure of the statement of the algorithm? Any questions about that structure? Where does K appear? K appears right over here. So in step 2, when we said apply G, we are not saying apply G only once. We're actually saying apply G K number of times. But we haven't really figured out how many times will that be. What's the value of K? How to determine the value of K and how is it relevant will become clear once we start doing the analysis of how this algorithm works. Right? How does Z naught work? Well, 2 parts, right? What does Z naught do? It's relatively simple. It's basically just flipping the sign in front of the all zero state. How does it work? Well, there's a nice simple matrix transformation. I'll reveal it in a couple of slides. It gives you time to figure out on your own as well. It's really just flipping the sign in front of the zero state and leaving everything else unchanged. So, identity for everything except for this one specific state. And on that one specific state, the transformation is relatively straightforward. I think that should give you a good idea of what the structure of the matrix transformation for Z naught would look like. Okay. Seems like everyone is fine. So let's move forward actually with the analysis of this. So we'll do actually 2 different kind of analysis of the structure of Grover's algorithm. Both of them are slightly, give a slightly different insight. Here on the top, what we've written out is kind of what you'd expect the circuit representation of Grover's algorithm to look like, starting from at time t naught to all the 0 end state. Recall step 1 was apply Hadamard to all those n qubits. So that's really up till here. This is step 1. Step 2 was apply G. In this formalism, what is G? G is everything that goes from here up till here. So this is G, right? And then we are saying, hey, this kind of block identifies for us G. Repeat G K number of times. So we will be repeating this transformation K times. And once that's done, step 3 said perform measurement to get your result. Right. In this case, well, whatever, not really, because I've got this, it's not a nice representation, but I've got these dots over here to say, well, it's applied some K number of times. But if you're really looking at the actual gates that I've drawn, yes, I've drawn K, the case for K equals 2. So hopefully you're okay with my loose formalism for the visual representation. And so you've got your G, you've got your ZF and Z naught here on the right-hand side. And I've got this nice 2D unit circle, which will come in handy in our visualization soon, about how we think about what Grover's algorithm is doing. So here's the foundational way of how we will treat and think about Grover's algorithm. Initially it seems like it's not clear where to start. And so for many Boolean problems, here's a nice place to start. We define a set A, which contains all binary strings of length n, such that the function f that we've been given encoded in the oracle evaluates to 1, right? And then the small a, we let it represent the size of A. In other words, this is representing for us what we can think of as number of good strings, right? Those are the strings that we would like as the algorithm to output, because on those strings, the function evaluates to 1. In the literature, that they're also called, these are the marked items, and we are searching for one of these marked items. Similarly, we could just define the opposite or the complementary set, all the length n binary strings for which the function f evaluates to 0. And small b then is the size of the set, and that then is the number of bad strings. We don't want to output a string that's in the set B. We would like to output a string that's in set A. Right? So now, rather than thinking about our original problem in this 2 to the n dimensional space where each dimension is its string, we have kind of projected down that entire space into just 2 dimensions. The space spanned by A is kind of one basis, and the space spanned by B is kind of the other basis. And so we are just interested in those 2 kind of directions. So imagine now defining the vector or the ket state A, which is just a superposition of all the good states. Right. And similarly, the ket vector or the state for the bad states. Oops, sorry, the label is off. This should be A and B. No, actually, that would be more confusing. Let's actually still just call them A. X. So X and A, X and B. And if you're okay with the intuition that I just mentioned, then what will happen in the algorithm is that we will always be able to think about the evolution of our state, i.e., the n qubits that we are evolving. We want to think about them as evolving in these 2 kind of basis vectors. We want to write them as a superposition of these 2 vectors. We don't originally know the size of A or B, right? Originally, we don't know necessarily how many items are marked, or what are the number of items which inputs for which the function evaluates to 1. We will do some assumptions when we do a later analysis, just for simplification, so that whenever it is sufficient, even if you don't know the number of marked items initially, the standard algorithmic presentation that we'll give for Grover's algorithm, there are just some additional post-processing items that you can add to it, which will suffice to take care of the fact that, hey, I didn't know how many marked items were there in this function f, right? But probably won't get to look at the details of that. Going back here, what we are now going to say is that for the purpose of our evaluation or analysis of Grover's algorithm, it is sufficient to think about the state as evolving in a superposition of these vectors A and B. And that really simplifies our kind of search space, right? We are not thinking about this 2 to the n-dimensional space and whatnot. We are just thinking about this vector A and vector B. And we are thinking how well aligned are we with A and how away are we from B. That's ideally what we'd want, right? And so, and as we've mentioned, for our purpose, we will always have alpha and beta to be real numbers. What will end, so theta traces the evolution to, in some sense, yes. Where does theta come from? It will become clear. Obviously, something to do with the evolution, with the unitaries that we are applying. But yeah, so theta will somehow trace how the state is evolving from its initial state to whatever happens after we apply g k number of times, right? And so the idea is exactly this, that rather than, it's sufficient to think about our state as evolving over the unit circle, where initially, let's say it's some vector in this unit circle, and we want to make sure that it evolves to being something close to A, and it rotates in some sense away from B. That's what we'd like to happen. So there's a 2 theta label over here that gives away what will happen. Essentially, if we apply G to psi, it will cause this rotation by 2 theta. Where does this 2 theta come from? We'll see very soon. Can we represent the evolution of the algorithm using Schrodinger's equation? For sure, I think at the end of the day, you take all these quantum algorithms and they can be stated in terms of evolution using Schrodinger's equation. But the purpose of presentation over here, and most quantum algorithms usually are presented just in terms of this unitary circuit gate representation. But you could always go back and I think that's actually what does and has to happen when you're thinking about physical implementation in terms of the many different implementation choices that you've seen. And I'm not at all an expert to talk about the details of those physical implementations, but in some sense, that's what it has to transform to in some sense, right? It's very much analogous to how we talked about in the beginning. When you're doing classical programming, you're writing your code in Python. That has nothing to do with the low-level code that the machine actually executes. It seems very divorced from the high-level code that you write. Yep. So you could literally take the entire evolution of the algorithm and write it down as an evolution of Schrodinger's equation over some time t. Yep. Although don't ask me to do that. All right. So everyone okay with this kind of way of thinking about our state evolution for the purpose of Grover's algorithm? We have identified two kind of subspaces spanned by vector A and vector B, and we'll be thinking just about these two subspaces. Right? If we don't care which vector in A we get as an answer, as long as we get something in A, we are good. Right? Okay. So let's actually see how this helps. What we've already seen is n-fold Hadamard applied to the initial 0n state will give us this uniform superposition state that I can write down as 1 over square root n sigma x. And I'll stop writing all the time x and 0, 1, n. You can understand that whenever I write an x, I mean a length n binary string. And I'll write down a short form notation that this entire uniform superposition state, I'll write as h. Okay. So we're defining just this uniform superposition state as the state label h. Then what do? Well, go back to this representation we had in terms of alpha and beta. Right, so A was this uniform superposition of all the good states. B was the uniform superposition of the bad states or bad strings. Well, I can write h in this form as well in terms of A and B. So I can state h is equal to A plus B, but I need to figure out what are the amplitudes in front. Based on what we know, could you figure out what the amplitudes in front of A and B will be? In the formula, since the initial value is zeros, can't x just be plus? Well, this is not a single qubit, right? These are now n qubits. So it's a plus state would be just 0 plus 1. So this is plus tensor n. Yes, you can write it like that. But since we'll be playing around with binary strings a lot, it's more helpful rather than writing plus tensor n to really write it as a length n binary string. Right? So it's not arbitrary. It's actually us saying that, hey, this is a uniform superposition or all length n binary strings. Correct. This is just a logical partitioning or rewriting of this uniform superposition. But what would be the amplitude in front of A? It's not just 1 over square root of n, right? Because we are not saying it's just one state, right? A could be many states. So capital A could contain many states in superposition, if you recall our representation, and capital B could contain many states as well. So we'll need to take that into account. And Emma got it right, and so here kind of mentions it as well. So we take into account the fact that there are small a number of states in capital A. So we have this a over n square root, and similarly b over n square root as the amplitudes. So this then becomes our logical partitioning of, this is normalized, right? So this then becomes our rewriting of the uniform superposition, but it's a much more meaningful representation now. So now what we need to do, if you recall Grover's algorithm, we're done with step 1, we need to apply step 2, but now we are kind of slightly in a better position about how to talk about applying step 2. So we want to figure out, as part of step 2, what will happen if I apply G to A. What is that equal to? And similarly, I need to figure out what is G applied to D. Right? Now, before we move forward in evaluating this, let's go back and quickly rewrite or figure out what is a matrix representation for Z naught. So Z naught, recall, is written or is described by this definition. Based on this, what would Z naught look like in terms of its matrix representation? Right, so people who kind of forgot, this is what Z naught is. Excellent. So it's just the identity matrix with the first entry set to -1, right? So it says 2 to the n size 2 to the n identity almost, where the first entry is -1 and everything else on the diagonal is 1 and everything else in the matrix is 0. Right, so this is Z naught. Let's also rewrite it slightly in Dirac notation, which we haven't really done before, but now is a good time as any. So this entry can also be rewritten as this. Right, and this might be new for some of you, which is just an outer product, where if you're taking this to represent a ket, i.e. a column vector, then this represents a row vector obtained by taking the transpose of your ket. So just take the ket column vector represented by 0n, takes its transpose. For our discussion so far, we are assuming real entries, so you don't want to have to worry about complex numbers. So you just take the transpose of that. Now recall what's the difference here. Had we written this in this form, then that's your inner product representation, right? Or in Dirac notation. However, this is the other way around. And so you're multiplying a column vector with a row vector, and that results in a matrix. So this gives you a matrix. And actually, this gives you a matrix with just a 2 on this topmost entry with a minus sign over here. So you just get this -1 as a result of the simplification, right? So hopefully, this is a nice way to represent matrices in Dirac notation. Okay, so with that, let's evaluate GA and GB. Right. So we've got all the nice information on the right-hand side over here. Let's evaluate GA. So what does GA look like? G applied to A, let's just write down all of G, is minus H tensor N Z naught H tensor N ZF applied to A. So what can we say about minus ZF applied to A based on this information that we have on the right-hand side over here? Minus Z sub F applied to A should equal what? It's a nice simple observation. Note Z sub F is defined by this, so it's just a 1-9 representation. You just take F, evaluate F on the exponent over here in front of A. Recall was the good strings. Good, exactly the right question to ask. A corresponded to the good strings, i.e. f of x evaluates to 1. So you get -1 to the 1, i.e. -1 in front here. But then over here, I'm evaluating minus Z sub f. So that will give me just as output then what state? Excellent. I just get A out. So what I'm essentially going to do then is to say, hey, let's take the ZF with the minus sign and consume that by writing this as now H tensor N, Z naught H tensor N, A, based on the observation we just made. Right? Now we all have a nice representation for Z naught as well. We can write it out. So you want H, Z naught H, right? This thing is going to equal H. Z naught had the representation identity minus 2, 0n, 0n, H, right? So now I can just evaluate this out to simplify it. For the identity case over here, recall that H is self-inverse. So when the two H combine together, they cancel each other out. So I'll still write it out and then mention it. H tensor N times H tensor N. This part will evaluate to identity as well. But then I have got minus 2 H tensor n applied to 0n, and 0n and H tensor n being applied from the other side. We'll talk very soon about what Z0 is doing and how to think about the intuition behind what Zn is doing. Let's simplify this calculation a bit, and then we'll think about what the purpose of Z0 is. How could I simplify this expansion? Well, I just know for the first part, it's relatively obvious. Well, this thing becomes identity. And then I make the observation that, hey, this thing is exactly the definition of the state H. The variable X represents a binary string of length n. Right? So whenever you see X, X is an element of length n binary strings. Right? What was the purpose of expanding it out in this formalism? We know that this thing then is exactly the label H. H tensor n applied to the all zero state gave us the uniform superposition state. That's we labeled concisely as H. So we get I minus 2 H, and exactly the row vector for that from the right-hand side. So it's a very nice, simple representation for this relatively more complicated looking thing, right? Cool. So we've got a minus sign there, right, Victor? Other than that, you're right. Okay, so everyone okay with how we got here? Now we're in a position to actually evaluate G of A completely. So we have G of A equals, we take the definition that we came up with, I minus 2 HH. And this, I think, is one of the nice calculations where the power of Dirac notation kind of shows up as well. You want to calculate this thing. That's relatively straightforward enough. Identity times A gives us A, and then you've got minus 2 H A. But then now, rather than doing some bulky matrix vector calculation, you know, hey, this thing is an A product. So you're essentially just going to say, hey, I've got the vector H over here with the amplitudes in front being determined by this inner product between H and A. We know A, we know H, so we can actually explicitly do or calculate this inner product. Let me rewrite this to make it kind of more obvious. This is equal to A minus 2 H, and then H in a what did I do? So this square root of A over N is the contribution from the inner product. We know because recall A and B, good question, if that was not obvious. How do we know that A and B are orthogonal? Recall the vectors in A and B are exactly disjoint. The set A contains all the bit strings for which function f evaluates to 1. The set B contains all the bit strings for which f evaluates to 0. So all the vectors in there are already orthogonal by definition to begin with. So A and B have to be orthogonal then. Right. So where did this come from? This square root of A over N is just inner product between H and A, because that's the amplitude in front of H, in front of A in the expansion of H. And then we just rewrite the state A as well. State A is square root of A over N, A plus square root of B over N, B. Right. Simplify this out, and we get 1 minus 2A over N, A minus 2 square root of AB over N, B. Okay. Right, so we made good progress here, right? We've got a very nice representation of what happens to the good states, to the good strings, once they undergo evolution by G once. we can repeat this calculation now with very similar kind of calculations to figure out what G does to B. I'll just write it out for you. So we have G applied to A gave us 1 minus 2A over N A plus 2 square root of AB over N B. I won't do the calculation, you can verify. Similarly, GB will give me a unit similar kind of superposition, naturally with different amplitudes, as one might expect. 2 square root AB over N A minus 1 minus 2B over N B. Right. So you've got transformation in just 2 dimensions by A and B. Let's write it down as a matrix M. So what is the matrix transformation being kind of achieved by G? If you imagine this as a transformation from in the space of spanned by B and A. So imagine the column headings over here being B, A, B, A. And based on the above 2 states over here, let's just fill in the entries. What will be the entry over here from B to B? What's the amplitude for that? It's one of the 4 entries we've got above over here. So the amplitude, transition amplitude kind of from state B to B is just this amplitude in front over here, right? 1 minus times all of that, right? So you'll want to take them out. Don't forget the minus sign. So you've got minus 1 minus 2B over N. And similarly, you can read off all the other entries. You've got minus 2 square root of AB over N. You've got 2 square root of AB over N. And you've got 1 minus AB, 2A over N. Oops, sorry. Oops. Okay, so now for one big kind of observation that's like, the first time you see it, oh, that's awesome. I wouldn't have thought about it. We've kind of already given it away. In our visual representation of the unit circle, you can verify that this matrix is also equal to I'll leave this as a calculation for you. And what is this doing now? If you forget about the square, so I'm saying this matrix square is this matrix, and this matrix M represented what G did to states A and B. But this smaller matrix over here that I'm squaring over here has a much nicer interpretation. What is it? If you just, yeah, it's you can just see the theta running around in there now, right? So this is nothing more but a rotation matrix squared. So that's kind of saying then that the net effect of applying M or G once in this case is kind of rotating or doing a rotation twice of this matrix. So that gives us insight in terms of where that 2 theta was coming from, where the theta now is obviously going to depend on this B and A. And that will then lead us into our analysis for how should K depend on A and B. Right? Everyone with me on this kind of connection? How to obtain the small matrix at the right from the large matrix on the left. I would recommend you go the other way around, right? So you start off with this matrix, multiply it out with itself, compute its square, and then you get this matrix. The insight of the analysis is, in fact, exactly indeed the other direction, but it suffices for us to make this observation as well, right? So you take this matrix, square it, and you get this matrix. Okay. So we want sine theta to be equal to, or we have sine theta equal to square root of A over N. and we have cosine theta equal to square root of b over n. Right. So the initial state h that we had now is parameterized in terms of theta as cosine theta b plus sine theta a. Right. That's just changing the parameters. Hermitian operator is multiplied to the conjugate give identity. So should this be the case? I'm supposing all the operators are Hermitian. Well, I'm applying a rotation matrix if you want to think about that, right? So these are, so initially what we had were unitary matrices, and then within those unitary matrices, I got the interpretation of that entire transformation as a rotation matrix. So for Hadamard, we have this nice connection that Hadamard indeed is unitary and is Hermitian and unitary, right? So it's not necessarily that all these unitary matrices will be Hermitian. Okay. So what will be now the evolved state after k applications of G, right? That's what we want to now analyze. If we apply kg times after k applications of G, the state H has evolved to right. So if rotating it once or applying G once meant a rotation by theta twice, and we are doing a rotation k times, or we're applying G, sorry, k times. So the entire state then becomes 2k plus 1 theta b plus sine 2k plus 1 theta a. Right. Everyone good? Why is it 2k plus 1? Because initially we already have this state before the application of G. So we already have kind of that parameter theta once. So that's the plus 1. Then where's the 2k coming from? Well, because as we already noted, the application of G is a rotation by theta twice. Then application of G k number of times will give me a rotation by twice that amount. So that's the 2k theta. Right. Now, what's our end goal? Our end goal is to get as a measurement result something that is with high probability in the subspace spanned by A, i.e., I would like an element of the good vectors or a good string. I want a good string as an output. So what would I like to analyze? I would like to analyze the situation when sine 2k plus 1 theta is approximately 1. Right? That's what I'd like to get. So we want sine 2k plus 1 theta to be approximately equal to 1. That's a key goal towards that end. So that implies then 2k plus 1 times theta is approximately pi over 2. Right, so your basic trig identities. So k then is approximately theta divided by 4 pi minus a half. Right, but recall from our original definition, sine theta is equal to square root of a over n. Right, so let's plug that in. That theta is equal to sine inverse of square root of a over n. Oops. For our current analysis, as I mentioned earlier, you can do additional post-processing analysis to figure out what kind of things happen when the function has multiple number of states labeled as or evaluating to 1. For our current evaluation analysis, let's assume we fix a equal to 1, i.e., in some sense, the hardest case, where exactly a single entry in the entire 2 to the n set of possibilities evaluate 2 to 1. Right, so we were looking for literally one needle in this entire haystack. So just for our current analysis, let's assume a equals 1. So that's equal to sine inverse. So that means we are looking for sine inverse square roots of 1 over n. we are doing the asymptotic analysis, so n is large, so that we get then that theta is then going to be approximately equal to square root of 1 over n. Right? For a large n of n, square root of 1 over n is small, so we can apply that identity, take this, and then plug it back in over here. And from here we get then that k then has to be equal to the floor of pi square root of n over 4. Let me write down. Where what has happened then is that we have finally shown the square root of n appear as a kind of requirement on k. What have we kind of, we've done lots of kind of relatively straightforward math. What is it saying? What the specific analysis that we've done is, if we assume that the function that we were querying had only one marked item, i.e. there is literally exactly one input for which the function f evaluates to 1, in some sense the hardest situation. If we do that analysis, then the number of times I expect to iterate the algorithm's main unitary g, which was parameterized by k, how many times should g be applied such that the probability to get a good string as output is nearly 1, then we are saying that the number of times k should be applied is order of square root of n. And that then goes back to our initial result about what Grover's algorithm provides as an improvement, that if I am querying an oracle, then in square root of n number of queries, in this analysis, assuming there's only one labeled item or marked item, then in order of square root of n number of queries with high probability, I will get exactly the marked item out as a measurement result of the 3 steps that were identified by Grover's algorithm. The floor function is coming, well, the approximation is coming from here, and then the floor is coming because we've dropped the minus half, right? So that's what's bringing in the floor. But don't worry about the constant factors. We've got kind of the bigger order dependency, right? So it's square root of n in terms of the asymptotic complexity. For algorithmic analysis, you've got this field called complexity theory, and in complexity theory, you'll generally be doing, so whenever you see these notations of the form big O of n, omega of square root of n, we are already assuming that we are doing an asymptotic analysis for input size as it approaches infinity, i.e. how does the algorithm behave for large input sizes? That's already kind of a key built-in assumption in all complexity theoretic analysis usually. So taking that assumption is fine for large n. Right. To superpose and apply the search function once, and then, so let me understand the proposal. Why can't we simply put the entire list of our items data points into a superposition, which we did, and then apply the search function once and then measure? Right. So think about what was just proposed. We are what we in fact already did over here was indeed perform a uniform superposition, and after that, if we just apply z sub f, z sub f will evaluate the function and put down kind of a -1 instead of a +1 in front of all the label entries. But now if you think about the probability of measuring them, it's literally still 1 over n for all the items. So the standard naive approach that one might expect, hey, take the uniform superposition of all possible entries, apply my function, and then measure. It's a good kind of thing to check that won't work at all, because by applying z sub f, the only thing that you did was flip the sign in front of all the good items. That doesn't make any difference for us in terms of getting the final probability. The final probability is still kind of a over n for the good items, b over n for the bad items. Good observation, yes. In our current, if you don't do this analysis in terms of what's a good k, which we actually haven't done yet as well, right? We have only done it for a single item. Usually the analysis would work along the lines of, if we assume the number of marked items are this many, then k has to be so much in order, or k should be this number in order to guarantee that we are maximizing the probability of getting a good item out. We can for sure over-rotate in Grover's algorithm. So if we choose to keep rotating, i.e. keep applying G, thinking, oh, we'll keep getting better and better and better. No, that's not going to happen. For sure, there will come a point where, so you started out with something that's close to B, you kept rotating and you kept getting closer and closer to A. You didn't realize, oh, I should stop here. And then you kept rotating and you'll keep going now away from A and again, now closer to minus B. So that kind of analysis does have to come in Grover's algorithm. In fact, I'll end today with a question along those lines as well. And so if we don't measure and we kept just applying G, then for sure there's no measurement, no collapse of the wave function or the quantum state, and we just keep performing this rotation again and again. So we don't measure the approach to it, but we can determine how many times we should apply G by determining this bound on K. And that would then depend on what do I assume about the number of marked items. And so there's a little bit more of post-processing analysis that we won't discuss today. But if you pick up any good discussion of Grover's algorithm, that will have additional details about, well, how can I repeat Grover's algorithm such that even if I didn't know the number of marked items, I get a reasonably good bound on my analysis of, hey, try K this many number of times. If that didn't work, try K for this many number of times. And then you can show with high probability that you'll hit a marked item soon. Would this be a time-independent approach given we don't have any impact of time pace for applying the G gate? Ooh, I'm not exactly sure what time pace would mean over here. So one issue would be exactly right, that given the complexity of your state, that would apply some physical limitation on how quickly you could apply these transformations. What exactly are the bounds or limitations coming from that physical details? I wouldn't know. Maybe someone from the participants or the mentors would be able to give those details. So it's possible to rotate till, say, 2k plus 1 theta, which may be more accurate, but requires us to. Right. So the idea is, depending on the number of marked items, you'll have to repeat some number of times. You can for sure determine an optimal K. And then there are different choices of K which may or may not be good. So there's a. So if there's a question that I've missed in the discussion, I'm not sure. Maybe you could repeat it. By the number of marked items, I mean the value small a, the number of inputs for which the function evaluates to 1. Okay. So kind of to wrap this up, this bound over here implies then that Grover's algorithm works in as O of square root of n. And we can prove that this is optimal. You can't do a better search, unstructured search even quantum mechanically. So Grover's algorithm uses a G circuit routine, which literally and simply performs double rotation of the qubits until finding the good strings. So there was this initial Hadamard, but yeah, other than that, I think that summarizes nicely. So you've got this, you apply the G transformation to the uniform superposition state and figure out how many times you need to apply G such that the probability of finding a good string increases. How to translate unstructured data to Grover's oracle? Good question. We won't have time to discuss the details over here, but yeah, the issue is exactly, well, if I'm constructing this Z sub f, don't I already know what the marked items are? And there are good discussions in the literature about, well, what kind of application do you want to think of this as? In classical searches, we always compare with the answer. In quantum search, we're only applying the G gate K times and hope it matches. So perhaps what was implicit over here is after doing all this after doing all this transformation, figuring out that this circuit should be repeated K number of times, I will do a measurement. I will get out some string X prime. Then for sure, I would want to do it, because this is not a deterministic algorithm, the algorithm that always gives the right answer. I would want to check it via verification. Hey, for this X that was output over here, let's evaluate F on that input. Do I actually get 1 or not? So that verification for sure should and can be done trivially. Would there be a time independent Schrodinger? I'm not sure about the time independent Schrodinger equation formulation. I think the dependency on time here would come in terms of the state complexity, but someone can correct me if I'm wrong. The lot of times here, so when you say we would repeat this a lot of times should be compared against the actual complexity, right? So we are saying that the lot of times is bounded by square root of n. So we don't actually, so this is not a situation where I will leave you with a question where you will actually show that in a specific case, Grover's algorithm will actually work with certainty. And so you don't even need to repeat the algorithm twice in that specific case. Range of n value, and so n is the number of inputs, right? So you've gotten a function f. The function f itself is defined on n bits. So that determines what the value of n is. How do we know exactly where we are starting on the unit circle? Just by definition, right? So the way we've constructed our representation of A and B, the initial superposition for sure will have to be in quadrant 1 because all the amplitudes will be positive in the initial construction of state H. Or can we stop the algorithm before if we find the right value? Well, the whole point of K is to optimize the probability of finding the right value. As you'll do the analysis and in the exercise question that I've given as well, for sure you can play around with, because in the analysis we've done, we knew a priori that, hey, we've only got one marked item, hence it makes sense to optimize for K. In the general scenario, we won't know how many marked items are there. And then the strategy over there is something exactly kind of corresponding to, hey, let's assume the order of marked items are, let's say, n over 4. Apply this algorithm for some number of times based on that assumption, run the algorithm, get the output. If that output doesn't work, change the assumption about how many marked items did you assume, figure out the corresponding K, then repeat the algorithm. And when you take that analysis and take that kind of process and do the analysis for it, you still get an O of square root of n runtime for this algorithm. So we can essentially generalize the temporal evolution. All right, so there's some questions about the physical implementation stuff or time-dependent evolution using Schrodinger equation, which I think other people might be better able to answer. I'll leave you with one more interpretation or insight into the algorithm, which you'll find in the notebooks as well, and which was kind of the original motivation, kind of insight into the algorithm. We have thought about the algorithm in terms of rotations. Here's another kind of the classical interpretation or intuition about the algorithm in terms of inversion around the mean. It's again kind of a logical, slightly different logical partitioning of the G unitary. So we break up G into U times Z sub F, where U is this transformation. Note what's different is that this minus in our kind of calculation, we kind of attached with Z sub F. Rather, we have now attached it with U, and we know that this kind of changes the matrix representation slightly to this of this matrix U. So this is the all one matrix everywhere, right? And I'll leave that as an exercise for you to figure out how that comes around. Should be straightforward. What I'd like to do, though, is now figure out how the state evolves under this kind of logical partitioning of G in terms of U and Z sub F. So let's quickly run through that. So if I have U and applying that to a state in arbitrary superposition, let's not even assume A plus B superposition. Let's assume U is being applied to some arbitrary state in sigma x alpha sub x x, right? So that can be written as sigma x alpha x, bring in the U inside. Next, we've got a nice matrix representation for U that we can use in this construction. So that's going to look like sigma x alpha x, oops, not 2, alpha sub x. And then you've got 2 to the n, the scalar multiple in front of the all one matrix. right? Minus identity X. Again, a question from the exercise that this entire thing can be written as sigma x2 mu minus alpha x, where what is this mu? This mu is nothing more but the mean of the amplitudes. It's a quick observation or calculation that you can do to verify this. Note that this now is kind of giving a really different insight in terms of what the algorithm is doing and how it is behaving. I'll talk about that shortly, but like, let's just make sure I understand what's happened, that the entry in front of each of this X has become this thing where we've got this 2 times mu minus the original amplitude in front of it. And that's what usually is referred to as inversion around the mean. Let's visualize it. What is it saying? So now the visualization that we'll have is not in terms of rotation between A and B, but rather in terms of this inversion. So this is the initial setup, right? Our state H in uniform superposition. Let's say X star over here is the marked item, the labeled item for which F evaluates to 1. I apply Z sub F. Well, Z sub F just did one thing, right? For the marked item, Z sub F of X was going to give me minus 1 F of X. So the only thing that Z sub F actually attained, you know, one might have assumed Z sub F was much more complicated looking thing, but it's kind of doing something very similar to Z naught. Z naught kind of fixed the location where the sign would get flipped. Z naught said always flip the sign in front of the zero state. Where Z sub F has this dependency on F, where it says, hey, flip the sign in front of the marked state. In this case, we are assuming a single marked state. So applying Z sub F has done essentially this. Everything else remains the same in terms of the amplitudes, except for the amplitude for the marked state becoming flipped. Now, logically, what has changed is that the original average or mean alpha has changed into something alpha bar, which is slightly lower because, well, one of the entries has become negative. We use that essentially to our advantage in this algorithm by basically then applying what we rewrote as U times Z sub F. Z sub F has already been applied. Now we are interpreting what U is doing. And the application of U in front of the marked state is going to apply or is going to change the amplitude into 2 mu minus alpha sub X. So whatever was the original amplitude, negate it and add to it 2 times the average of the original thing. Let's kind of work it out explicitly. So the original average was 1 over square root of n. Let's take it as that, 1 over square root of n. This is a slight assumption over here, but it's good enough for our purpose at the moment. Minus alpha sub X after the sign flip is minus 1 over square root of n. Right, so we've got this thing. And so you get 3 over square root of n. And so that's what Grover's algorithm has attained now in terms of amplitude amplification. Right, so when we were rotating from A to B, the insight over there is we are increasing the amplitude of, or hence the probability of getting as a result something in A. Here we are seeing exactly that analysis in a slightly different visualization, that what is happening after each iteration, each application of G is that we, as a first step, invert the sign of all the marked items. That decreases the overall average of what the mean of all the superpositions. And then this operator U performs this inversion around the mean, which results in all the amplitudes which had gotten flipped becoming positive and increasing their magnitude. And we can now keep repeating this procedure such that overall, in the first application of G, we got 3 square root of n. You now start with this situation and say, let's say we are applying Grover's algorithm with k equal to 2. So we start with now this state representation. Again, apply inversion. So this will be the result of Z sub F. Inversion around the mean is lowered even more, such that now when I apply U, the new amplitude will be, rather than 3, 5 over square root of n. And this will keep kind of increasing. Now, this analysis in of itself would be kind of misleading to say, oh, would this mean this will converge to 1? Well, kind of, yes, it will attain some kind of probability amplitude close to 1. But then if I keep applying G, very soon something else will happen, and which I recommend you to work out. And then this amplitude that was being amplified starts decreasing again. That amounts to, in our rotation visualization, where our vector rotated close to A, and now we are over-rotating, and we are getting away from it, going away from A again, right? So these are kind of two nice visualization ways of thinking about what Grover's algorithm is doing. Okay, so that's all I have in terms of explanations. I leave you with 2 questions specific to Grover's algorithm. So let's do kind of an opposite side analysis, or I'm asking you to do it. So in our analysis, we took the number of marked items to be exactly 1. Let's assume it's exactly kind of the other scenario, in the sense that there are exactly half of the items are marked. Half, there are, for n bit string input, exactly half of the input strings evaluate to 1. For this situation, figure out what is the probability that an algorithm, Grover's algorithm, outputs a good string after just a single application of it. Right, so that's a quick, straightforward calculation, given that you were following our calculations. But then the more interesting question is, assume we still have got the same function f with half items marked. Could you figure out a modification to Grover's algorithm? So now actually it won't be Grover's algorithm itself, but we will actually end up slightly modifying Grover's algorithm. How? That's the question. What should that modification result in? That modification should cause, as I mentioned in our earlier discussion, Grover's algorithm to actually work perfectly for this specific situation. So for the situation when there are exactly half the items are marked, there exists a slight modification of the Grover's algorithm, such that you can figure out one of the marked items using exactly one query to the oracle. Right, so this will require you to go back and think about our analysis of Grover's algorithm and what can be modified slightly in terms of the rotations, such that a single oracle call will suffice to get the right answer with certainty. Right. And with that, I'll finish and leave you with kind of what we started out with. Hopefully, all the discussions we've had about Grover's algorithm, teleportation, entanglement being used to manipulate information in circuits, is that the key thing that quantum computing is doing is allowing you to manipulate amplitudes and hence probability of your outcome results. And that's kind of the superpower being granted to you by quantum computing. And hopefully that's a perspective you agree upon. And that's all I have for you today. And that finishes QBronze for us. I'll just review other questions if there are any on Discord. How do you know if that X is increasing or decreasing the mean? Because X was positive when we flipped X for the first time, all entries were positive. Now a single entry, let's say if there was only one marked item, has become negative. So that would definitely decrease the mean, right? So you had all positive entries. Now a single entry has become negative, so the mean would decrease. The average weight of the red state is more than all the other states. So since K, or the number of rotation it takes to reach the answer, is dependent on N, how does that translate on the unit circle? So Shaurya, exactly as we've been discussing, that yes, we are doing rotations, and the amount of rotation we should do depends not just on capital N, but actually the property of F in terms of how many marked items are there. That actually allows us to determine how many rotations we should apply. And as if you do the question that I've mentioned, also that if I know in advance the number of marked items, then there might even be specific customization of Grover's algorithm that I could do that allow us to be even more efficient. And the reason kind of Grover's algorithm is really widely applicable is you can imagine this as a big generic routine in any quantum algorithm. So if you take classical algorithms, as I mentioned, the problem of identifying whether a Boolean formula has a satisfying assignment, it's the problem for the class NP. And in general, for nearly many computational tasks, this problem of finding a marked item or searching unstructured data is a very generic search routine. And so you've got this very generic algorithmic routine that you can plug in into any algorithm and get a quadratic improvement in the runtime. So there was a request about slides. Please note, if you go to Canvas, then the slides are uploaded in the files section. So the previous 4 lectures are uploaded, and I'll upload this one today there as well. The mean reminds me of wave propagation has so again, I'm not an expert in this, but I recall that Grover's original motivation came from something to do with so this U is something linked to or equal to the diffusion operator in crystals. So it very well, his intuition for that was exactly coming from there. So there very well might be more details over there as well in terms of the connection to wave function propagation. Right. So in general, we, if you take the original formulation of Grover's algorithm, where we don't know the number of marked items in advance, we cannot optimize in terms of k. But as I mentioned, there is a generic post-processing kind of routine that you can apply, which doesn't change the square root of n complexity of Grover's algorithm. Requires a bit more computation in terms of us repeating Grover's algorithm for different choices of k, such that with high probability you still get a marked item. So yeah, the point over here is not to represent kind of the plots over here were not kind of Dirac functions, but it was more along the lines that over here this is not kind of a continuous spectrum on the horizontal axis. Imagine each of these points as one of the bit strings, and we are just kind of plotting the amplitude on top of for that bit string. We don't have any amplitude weightage over everywhere else because we don't have the state as a continuous state, but rather just as a superposition of these 2 to the n different possibilities. Okay, I think that covers the question I've seen on Discord. If there are more questions, please feel free to put them on Discord. I'll keep reviewing them. Again, reminder for completing the requirement for QBronze, you should attempt ideally the exercises that have been provided to you in the notebooks. That's a good learning material. Much of what we discussed today within these slides for Grover, you can play around with interactively on the notebooks. Once you're familiar enough and confident with that, then move on to the quizzes on Canvas. And finishing off those 5 quizzes with each quiz with a greater than 50% score and an overall average greater than 70% allows you to complete the requirement of this bronze workshop. Right. Thank you.
Thank you very much, Jibran. Are there more questions in general about QBronze, as this is the last session with Jibran in QBronze? I am sure otherwise you will get back to them on Discord. Great. Thank you so much, Jibran, for this full lecture series, bringing everyone from the basics to Grover's algorithm. Great. I see Rashid joining. I will bring up a slide for what is coming up, because now you have a basis in quantum programming and you learned about some quantum hardware. Tomorrow we will learn more about quantum hardware. We will have Quantinuum with trapped ion quantum computing. And then 3 interesting career components are coming up. Tomorrow we will have Celia Merzbacher from QEDC, the Quantum Economic Development Consortium, bringing all stakeholders in the US and beyond in quantum together. She will give an overview of the quantum ecosystem and what is needed to join the quantum workforce. Her message is the quantum ecosystem needs you. Then on Saturday, we have an amazing career panel with several panelists in industry, academia, startups, to whom you can ask all your questions about careers in quantum. And then last, or almost last but not least, let me share my screen. Here we go. On August 1st, we have a great career fair coming up. This is the first of 2 career fairs. This career fair has many companies in Europe, in the US, and other parts of the world that will be there with their representatives, and you can join breakout rooms to interact with them and have one-to-one conversations. This is really a unique chance to interact with 15 companies in quantum computing, from hardware, software, supporting technologies, everything is there. There will be 3 steps to be completed to participate in this. The first one is complete QBronze before the deadline. So that means that this weekend you can complete your quizzes for the certificate and to join the career fair. The second, upload your CV. Also on Canvas, there is an optional module to upload your CV there. And you can indicate if you are looking for a job or an internship the upcoming year. Then 3, there will be a career preparation session on July 30th, where you get all the tips and tricks to pitch yourself and to write a great CV. And the day after, you can still upgrade your CV and re-upload it. So complete QBronze, upload your CV, and take part in the career prep session. And then this is your unique chance to interact with all these great employers. Rash, anything you want to add to this?
Yes, definitely, Malu. Can you hear me?
Yes.
Perfect. Hello, everyone. It has been over 10 days since we started the program, and what a wonderful 10 days that we had. So many people have come and spoken about their work, about their industry experiences. To begin with, we had William Hurley come and share about the direction of the industry. It was followed a few days later by the introduction to quantum computing by William Oliver from MIT. And what a great day today we had when we had the team from MIT give us a tour of their lab. So we were able to see people from all walks, from CEOs, from founders, from professors, from directors of quantum computing programs, and now the next generation of quantum researchers that we saw today during the lab tour at MIT. And even beyond that, we were able to get lectures from Shaima on quantum systems and quantum mechanics, Dennis Ruffler about the entrance of women and the importance of women in the quantum industry. We had the team from Keysight come and share about their work. From Polaris QB, share about the applications of quantum computing, especially in the pharmaceutical sector. And then we had Ricardo from Google come and share about quantum games. Then so many more. Today we had Shantanu from MIT. We had Marlu from NIST. We had Christian Prudence from Atom Computing. And then we had Elena from Blueforce share about the hardware that is required to make some of this quantum computing feasible and possible. And then today during the lab tour, we did actually see the dilution refrigerators from Blueforce itself being used at MIT. What a fantastic session, which was even made more fantastic by the presence and lectures by Jibran almost every day, preparing you, teaching you, training you in QBronze. The assignments and the testing for QBronze will be coming up. And for all of you who finish it successfully, you will get certification. And beyond that, what more can we provide to you? Great speakers, great lab tours, great lectures, great sessions, great training. What more? The answer is many of these companies, many of these labs, and many of these industries, they need young, trained, talented people. And that brings to the answer, the career session. It'll be coming soon. Keep an eye out. Many companies from across the country, from across the world, they want young, skilled, talented next generation of scientists and technicians to take this nascent and young field of quantum computing forward. And that is one of the goals of WOMANIUM, to train the next generation of scientific leaders in the quantum domain. That brings us to you. That brings us to this program. And Dr. Marlu has explained briefly the list of many companies that will be coming to the career fair and the career sessions. And from your side, you have to do your part to learn, to get prepared, to be ready for an industry that is ready for you. Any questions? Please share on Discord. Any additions? Please, Dr. Marlu, share.
There is one question. Abdelali Fargi asks, he already has a QBronze certificate. Is that sufficient, or do you have to retake the exam? Having the certificate already is sufficient. You can upload that prior QBronze certificate on Canvas. That also holds for equivalent courses, for example, Qubit by Qubit, the IBM Summer School, or university coursework. You can upload your proof of that coursework on Canvas, and that will be accepted. As you saw, there will be many companies that you know. IBM will be there, Blueforce will be there. In a later career fair, IonQ will be there, Quantinuum will be there. So many companies of which you have seen the speakers in the sessions will be there to interact with you. We will stay on for a minute if there are more questions in general.
If you have any questions, please do share it on Discord.
Our whole team has been working hard. This course started off with Raj that you see here, Rashid that you have seen many times, and me. And we reached out to all companies and then started building our team with more postdocs, more PhD students, more undergrads. And they have done an amazing job in organizing the career fair, in organizing the hackathon that is coming up. This will be very exciting. We have amazing challenges from Deloitte, IQM, Orca Computing, Quantinuum. Stay tuned for that. We will give more information at the end of the week. And with the help of this great team of volunteers, we have this course now. You as great active participants, many of you have joined already to help, for example, in the video editing team, posting summaries on LinkedIn, being active, answering each other's questions. And it is great how we all make this happen together.
Indeed. To add to what Dr. Marlu said, the program started as a brief set of discussions and ideas between Marlu, who was working at NIST, who still works at NIST and heads one of the leading and the coldest labs in the world, conducting amazing scientific research and development in the quantum domain. So always keep an eye on Dr. Marlu. There is a probability that someday she will become extremely famous, and it will be great that you knew her when she was doing the work and research. And from there, we created this program. And today we have about 1,000 people participating in this program, close to 100 teams and companies coming and participate in the program. Even then, as a small team, we would love to have more input, more feedback, as well as more help and support from your side, especially for some of the small things like Marlu said, video editing is a good one, but also certain additional areas where people ask questions on Discord. Many of you might know the answers to some of them. Please do answer it. It will create not only a better learning environment, but also will allow everybody to learn together, and grow this industry forward together.
And feel free to leave. The time of the session is over. We will stay on for a couple of minutes though, if there are more questions. For example, Amina Salami asks, what are the requirements for a CV? Can a high school student participate? The answer is yes. Among all of you, all of us, there are high school students up to industry professionals. Everyone can participate. Companies are very interested in young people who are still very open and can learn a lot to have them as interns and later on as employees. So put your highlights and what makes you curious about quantum and what you have achieved in quantum so far, which is already QBronze soon. Put that in your CV and fulfill the other requirements for the career fair and be there.
To add to the question from Amina Salami on Discord about the role of a high school student, it was during the discussion with Professor William Oliver from MIT, not during the main session, but during some of the initial interactions and discussions between the WOMANIUM team members and Professor William Oliver, that he shared that even for a university like MIT and a team like his, they look for young, driven, dedicated, talented young students. So starting at high school, given the fact that you're participating in this program, and also perhaps other programs will give you an edge, the kind of edge that people like Professor Williams and also his lab looks for. But beyond that, many of the companies, they also look for people with drive, skill, knowledge, and initiative. And Amina, the fact that you're here, it has already put you in par with many of the people who are much older than you, many of the people who have got master's and PhD degrees, many of the people with industry experience, but the quantum industry is still starting. So you have as much knowledge as anybody else. So we are glad that you are here. Even though you are in high school, you've got a long way to go, and this is a really good start. Thanks for being here.
Good you emphasize this, Raj. And what everyone has in common here is taking initiative. Everyone took the initiative to join this course, to self-learn in quantum. And this is one of the most important skills in careers and lives that will also appeal to the employers. Taking this initiative at a young age, amazing. Taking it at an older age, amazing. And this is what makes all of you stand out.
And that is what makes this industry grow. And that is one of the reasons why we showed you the lab tours. We showed you the people. We did not just share the science or the technology with you. We showed you the people who are working behind those things. And even for Professor William Oliver's video, which has been updated and uploaded to YouTube, we decided to keep those initial segments of interactions because it showed the type of human skills, the type of human attributes and qualities like curiosity, dedication, determination, initiative, etc., that people like Professor William Oliver brings to the industry, but also the quality that the industry needs. And those are all human qualities that we want you to learn from the experts, but also develop within yourself so that you can all rise to become the industry leaders or just leaders in any industry that you pursue.
There is a question, if we won't be able to attend the career fair, is there some other way we connect with the companies? I recommend you to sign up for the Flash Talks on Sunday and upcoming sessions. There you can highlight your own research or work in the quantum field, and this makes you stand out to us as an organizing team and ignites us to connect you with these employers. Please spotlight yourself, and then we can put you in the spotlight after that.
Great. And one more thing, we want to highlight you. We want to highlight the best of you to the world, to the industry, to the companies, and to the recruiters. One thing is to have your CV and also have the requisite skills and certifications. The other is, just like the MIT team made a video of their work, their research, and what they do, it would be great if you can create perhaps a 2-minute video introducing yourself, introducing your skills and capabilities in a nice, seamless video that can be shared with other participants so that they can learn about the skills and the knowledge and the personality that you bring, but also to the industry itself. Because ultimately, people make ideas which go and create new industries. And we want to empower those people so that new industries can be created and formed.
There are some questions about the lectures. We will post the ones from Jibran as soon as possible, so you can finish QWorld. And we have received several requests to post the videos sooner. So from now, for most sessions, there will be a live YouTube stream, and that will be saved, so you can watch right after. And then in the meantime, the video editing team that is now expanded, and not only Raj anymore, but also several participants can work on making a nice version. For today's lab tour, we are discussing with MIT if we can post it on our channel. We will let you know as soon as possible if that can be posted.
True. Thanks to all the people who have been volunteering and helping us with the video edits. So I wanted to give a little bit of credit to Owais from Pakistan, who has been helping us extremely and tremendously. Thank you, Owais. You have helped us a lot and making it possible to upload many of the videos, especially the video of Professor William Oliver, in time so that you could actually watch the videos just before seeing the lab tour. If no further additional questions, I think this is a good time to conclude today's session. For all the people who attended live, fantastic, thank you. You go to see the lab tour of MIT. We will have to wait and receive permission from MIT before we can share those videos online. So you got to see the lab tour, which the others will have to wait for a long time to see, unfortunately for them, fortunately for you. But you were able to see, meet, and interact with the people and the members from the lab. So fantastic.
Thank you for joining every day, and see you tomorrow with a talk about why the quantum ecosystem needs you, and an in-depth talk about trapped ion quantum computers by Quantinuum. Thank you very much. Have a nice morning, afternoon, evening, and see you tomorrow. Rashid is the one who needs to close the session. I need to run to the lab, and then we will see you all.
WOMANIUM team, switch off streaming, and then we will switch off Zoom.